Yeah. So this is joint work with my advisor, Avrim, at TTAC. And a little bit of motivation. So the set of complex objects that we might be interested in considering can be kind of like gnarly and hard to specify and hard to really understand. And so but the set of complex objects that are actually feasible given some sort of underlying structure might be a lot more tractable. And so some examples of this are you have a bunch of data points in high dimensions, but really they lie in some lower dimensional subspace, and so that's kind of the dimension of interest. Or for a more unusual example, you have some sort of piece of music, and it seems like it could be kind of arbitrary, until you realize that the first part is from song 1, and the second part is from song 2, and the third part is from song 3, and so there's a lot fewer options for what that could be like. And so in this work, our goal was to understand complex items through their constituent simple components, and in particular, do that in a model that I will define for you. And so in the rest of the talk, I'll define that model. I'll talk about this, what I'll call the learning task, and describe the task, give an algorithm, do some analysis. And in the standard dictionary learning setting, this is going to be similar to recovering the atoms of the dictionary. And then I'll talk about what we call the inference task, describe it, give an algorithm, and then give an extension, which is kind of what loosely ties this to the rest of the talks in this session in terms of the extension is in terms of robustness. And this is, the inference task is what is kind of related to recovering the weights in the standard dictionary learning setting. And so throughout the talk, I'll try to map back to the standard dictionary learning setting to motivate why we called this combinatorial dictionary learning. Okay, so defining the model. So we start with a bunch of objects and select some subset of them. So in this case, we had 6 objects, the sun and the clouds and the lightning bolt, and we selected some subset of a fixed number of them. And then we have a canvas, which we just think of as a vector, and select 4 locations, one for each of the images, one for each of the objects. And then kind of to map this to images in the real world, we have some sort of depth, and so we organize these objects front to back, and that means that you might end up with some sort of occlusion. So for instance, in this case, the sun is occluding the cloud because it is further closer to the viewer. So the abstract version that we're actually going to study looks like this. The set of objects is bit strings. So in this case, there are 5, and we're going to select, and the canvas starts off with a background that's a completely different color to the colors used in the objects. So we're going to select a subset of fixed size, so 3 objects that we're going to put onto the canvas. We're going to select the location, place it, location for the second object, place it. And now when we select a location for the third object, it's supposed to start before the first object finishes, and so we end up with occlusion. And this is going to be like the main technical challenge when it comes to actually going from these samples back to what objects generated them. And so, yeah, I just said this, like the thing that we just generated, we call a sample. Okay, so now we'll specify this learning task. So in this task, we are given a bunch of samples, and we want to recover the correct objects that generated them. And so like trivially, you could just say, okay, I have one object that's a 0, one object that's a 1, and then I can just put them all together and create these images. But our goal is actually to recover the actual objects that were used to generate this. And for this, we're going to use a property that we call W well-structuredness. And this property is similar to incoherence assumptions that are used in standard dictionary learning. And it basically says that if you take length W substrings of 2 different objects, they can't be equal. And actually, even if you take length W substrings of a single object, they can't be equal. And so we require that our object set has this property before we're able to do our learning procedure with it, or do a learning procedure to recover it. And so, like, really what we're saying is that the Hamming distance between any two substrings is at least 0 substrings of length W. Okay, so at a high level, the algorithm is going to first find pieces of objects in the images that we're certain come from a single object, and then stitch these pieces together to recover the full object. And so for the first part, we're going to rely on repetition. If we see something a lot of times, it's likely to come from a single object. And for the second part, we're going to rely on shotgun sequencing style algorithms that are sort of adapted from the computational biology literature. And so this is the statement of the algorithm, and we can work through an example. So here, the backgrounds are blue and the pieces of objects are kind of highlighted. And so the first thing we're going to do is collect all the pieces that we see. And then we'll discard ones that we don't see frequently enough. And now we're going to actually discard the ends of each of these because you can kind of have edge effects of like not knowing whether this extra bit on the end is a part of the object or not. And so we discard those. And now we have a collection of object pieces that we can pass into the sequencing algorithm. The sequencing algorithm is sort of just proceeds in a greedy way. It finds the section of largest overlap of at least W bits. And because we know that these objects are W well structured, if you have an overlap of at least W bits, then you know that they're from the same object and you can merge them. And so it goes through and does this. And then finally, we have to recover the ends, which luckily we can just do from the samples we already have. I'm not going to really explain this procedure, but we can just kind of go through and get them. Okay, and so the analysis for this is really going to rely on the fact that sequencing works if and only if the set object pieces covers all the objects. And so what we're really interested in is this question of, are all of these good pieces? By good, I mean that it should arise from a single object and not from overlaps of two or more objects. So I'm not going to go through the detailed probability calculation here, but you can calculate the probability of seeing a good string, and you can calculate the probability of seeing a bad string, and these are well separated. And in fact, they're well separated enough that we can define this p mid that's double p bad and half of p good. And then we can just apply Chernoff. And so the probability of seeing too many copies of a bad string is small, and the probability of seeing too few copies of a good string is also small. And then you can union bound over the number of bad strings and union bound over the number of good strings. And you can get the sample complexity, which is polynomial in M, the total number of objects, and S, the length of objects. But you might be disappointed that it is exponential in K. But unfortunately, this is kind of unavoidable because when you have the potential for occlusion by K-1 other objects, you sort of have to see enough samples to be able to see everything that you need from a given object. And also, I think it's reasonable to think of the world as having a lot of objects, but only a small number of them actually make it into the image. And so if K is like logarithmic in M, then, then we're good. Okay, so I'm going to talk about the inference task next. And so in that task, you're given a sample and a collection of objects that either you've already recovered or maybe they're the ground truth objects. And the goal is to give an explanation. And what do I mean by an explanation? I want to know that object B was placed at location 4 and object A was placed on top of it at location 6. And so there are kind of two different objectives you might care about. Maybe you're looking for minimal explanation, so how few objects can you use to explain what you're seeing. Maybe you're looking for a correct explanation, like what can I like commit to and say for sure was used when originally generating this image. And so for minimal, we talk about it in the paper. I can talk about it offline or at the poster, but in the next minute, I'll focus on the correctness objective. And so basically, this is also a greedy algorithm. You basically just find the largest string that matches a single object, and then for a similar reason to before, discard the first and the last bits of it. And you can kind of keep doing this and guarantee that whatever you find that's coming from, whatever explanation you find for the parts of the image is going to be correct. And so the very last thing is, okay, what happens if these objects have some sort of noise? And so for this, we define a stronger version of the well-structuredness condition called epsilon strongly W well-structured, where we once again compare two substrings of length W, but now they can't even be approximately equal. And so the Hamming distance between them has to be at least epsilon times W. Before it was just bigger than 0. And so now if we have that property, then we can kind of use the same inference algorithm with just a couple of changes. Now the objects, like I said, have to be epsilon well structured. And now instead of looking for exact matches, we can look for approximate matches, and we can recover, we can correctly recover an explanation. So I just wanted to quickly say how I think about this work, because I think there are a couple different ways to think about it. So first of all, I think these problems feel like very fundamental theory problems in their own right. Just like how do you kind of decompose a string into substrings that you can make sense of. But also, I think it's a complication of standard dictionary learning, which really is often linear and looks at linear combinations. And then maybe it's a framework that could be explored more. Maybe there are other generative models that we can think of these tasks for, or maybe we can think of other tasks with this generative model. And especially the robustness piece is something I'm kind of interested in thinking about more. So yeah, happy to chat about that. Thank you.
How big should I think of W as being, and where did it show up? Did it show up in the bounds for the well-structuredness?
That's a good question. W is logarithmic in S, and then S showed up in the bounds.
Okay. I wasn't sure how big it was. Can you remind what all the symbols here are? What's K, M, and S?
Yeah, K is the number of objects that are in an image. M is the total number of objects in the universe, and S is the length of the maximum length of an object. So actually, the reason you can think of W as logarithmic in S is because if you have a random object, log S is about the number of bits that you need in order to distinguish.
Sure, makes sense.
Yeah.
Concretely, are there do you think are the most interesting open problems to study for this right now?
I think kind of extending, we just have the one result on any sort of handling of noise. I think thinking more about that would be interesting.
So even defining another appropriate notion of noise and studying it. Yeah, okay.
Yeah.
Cool. Any other questions from the audience?